Today we will see some more evidence of how the periodic table of chemical elements is tied together with the HR diagram and evolution of stars. We will also learn how quantum physics ties together with all of these. First though, a reminder of our last lecture. Click back and forth between the HR diagrams on the left as they switch back and forth. As you do that, try to choose the answer on the right. Notice that one of the HR diagrams is a regular one where the stars are at 32 light years away. The other one is an HR diagram where basically we put the stars according to color on one axis and brightness on the other, but at an unknown distance. Next comes a diagram that will actually serve us as some kind of a tool. You will see this diagram again in a few slides. Now, do you recall that arithmetic exercise that I have given you last week? I asked you to find the mass of 4 hydrogens and compare it with the mass of 1 helium. We found out that the missing mass can be given off as energy according to E equals mc squared, Einstein's famous equation. For our purpose, we will call this the binding energy. It's very much related to what will be defined here as the binding energy. Since there are 4 nucleons, 2 protons and 2 neutrons in helium, you had to divide the difference in mass by 4 multiplied by speed of light square, change into the appropriate units, and the number would be 6. That's the number in the graph. And that's the number represented by the difference between helium 4 and hydrogen 1. Now, if you add 2 neutrons and a proton to helium 4, for example, you're going to get lithium 7. Notice that this would cost you energy. So in the hearts of stars, in the cores of stars, there is no helium to lithium burning. C12, however, is higher up than helium 4. Notice that C12 means carbon 12. That is a nucleus with 6 protons and 6 neutrons. That has higher binding energy and therefore less mass than that of 3 heliums that were put together. Now that's carbon 12. There is also something called carbon 14 that's different than carbon 12 and not represented here. It's fairly rare, but on Earth it's used in finding the age of objects that are thousands of years old. Carbon 14 is made of 6 protons and 8 neutrons. In chemistry, the number of protons determines the name of the chemical element. Elements with different number of neutrons than the regular number are called isotopes. In the previous lecture, I mentioned the helium flash. When helium 3 form carbon. In that lecture, what I did was that I assumed that this process is happening very quickly. As we will see in the next slide, and combining with this specific graph here, where you go from helium to carbon, carbon to oxygen, etc., we will see how this relates to the stages right after the helium flash. So here are a few more details about the life of a star like our Sun after it became a red giant and went through the helium flash. My simplified version was that the helium flash pushes the outer layers, driving them away, leaving a white dwarf behind. I kinda skipped 50 million years along the way. Stages 9 through 12 in the table and the book have these details. These are the result of that binding energy graph in a previous slide. The helium flash, rather than heating up only the outer layers, also heats up the core itself and make it grow larger. In a process, it lowers the density and the temperature, and so no more helium is turning into carbon after a while. This tug of war between gravity and pressure continues for a while in the horizontal branch and AGB stages. Each time the core expands and cools, fusion into carbon slows down, and there's a little bit more of fusion in outer layers of still hydrogen to helium. Then the whole thing contracts. In principle, this cycle can continue, and sometimes it does continue in those horizontal branch stages. Then there's more helium to carbon, and that can then be a whole long process of helium turning to carbon, and then oxygen, and then heavier elements. When that process is very efficient, the Planetary Nebula and the leftover white dwarf are formed. Basically, that happens when there is enough fusion into carbon, so that slowly the whole outer layers are thrown out slowly, and when the core with the white dwarf is exposed, those outflowing winds are illuminated and shine, and that's how we see the Planetary Nebula. Now, that corpse called a white dwarf star has been a mystery for a while. After all the helium turns into carbon and oxygen, the mass of the core is of certain mass that's under 1.4 times the mass of the Sun. The Planetary Nebula formed, the material outflows, and we have exposed a white dwarf of surface temperature of order of hundreds of thousands of degrees and slowly going down, density that is 10,000 to 10 million times that of the Sun. But how does this hold against gravity without any new source of energy? Funny you should ask. End up that what holds it against further collapse is called quantum pressure. This idea combined the work of Werner Heisenberg, a German that was afterwards involved in the atomic bomb project of the Nazis, Wolfgang Pauli, an Austrian deist from a Jewish family, and Ralph Fowler, a World War I veteran that got seriously wounded during that World War I that started exactly 100 years ago. Heisenberg came up with something called the uncertainty principle. It said that small particles, let's say an electron, can't be squeezed into regions that are infinitely small. If they are, they respond by speeding up. That's how they create an effect that's similar to the pressure in stars that we explained before, in which we said higher temperature make atoms move and collide with each other, creating pressure. In this case, the pressure is created just by trying to squeeze those electrons into a small region. Wolfgang Pauli, a few years later, has shown that it didn't even need to move. Electrons in atoms are organized in such a way that, for example, 2 electrons of helium fit nicely in the same orbit, provided their spins are opposite. In the periodic table, there are elements called noble gases, for example. They all have such paired electrons in the outer shells. Fowler then applied the idea to white dwarfs. What Fowler has shown is that this is kind of similar to parking your car in a parking lot, with a bizarre twist. Okay, if there are lots of free spots in the parking lot, think about lots of electrons, then you can easily find a spot, no pressure there. I know it's a little bit of an analogy, but at this stage it's going to be a little tougher to explain that analogy. But in the analogy, it's fairly easy to find a place, no pressure. However, if there's one single spot left and lots of cars kind of fighting for it, there is pressure and maybe lots of collisions as well. Now, in Pauli's twist, you have in every parking spot 2 cars, one on top of the other upside down. That's the spin up, spin down of the electron example. Now, as a result of that, when you put a lot of particles into a tiny region, mass of the sun into the size of Earth, that makes for the very packed parking lot and enables there to be that quantum pressure to hold against collapse, at least until you reach a certain limit. That limit, which is just a little over the mass of the sun for the core itself, was explained thoroughly by a young guy by the name of Subrahmanyan Chandrasekhar. At the end of the Roaring Twenties, astronomers found that masses of white dwarf stars were never more than about the mass of the sun, or just about there. Why should there be? After all, some stars in the main sequence were hundreds of times more massive than the sun, with cores that were at least tens of times the mass of the sun. Why wouldn't those cores become observed white dwarfs? Comes in Chandrasekhar. As my teacher in graduate school used to say, in the 20th century astrophysicists had great ideas and they played with them on backs of envelopes. Then Chandra did it right. Chandra wasn't the first to suggest that there is a limit to the quantum pressure that holds the white dwarfs, but he was the first to do it right, including all fields of physics known at the time. He proved that quantum pressure wouldn't work for a core above 1.4 times the mass of the sun, and basically after you reach that, the pressure inside decreases as you add more material. As a result, it would shrink dramatically. His ideas were met with complete horror by Arthur Eddington, the most respected astrophysicist of that time. He was respected because he proved Einstein right only a few years later. Here's what Eddington said. What Chandra found means that cores would shrink out to just a mile across and even radiation wouldn't escape, which is of course the idea of a black hole. Then Eddington continued to say, I don't think nature would allow that. His fame made Chandra's work obscure for a while. He was a slight 19-year-old graduate student from India. He became obscure for a time despite his brilliance. Luckily, the University of Chicago started their great general education program at the time and hired him. Chandra stayed there until his death in 1995. He won the Nobel Prize in 1964. I was fortunate enough to hear his wife describe him in a conference in his memory in 1995, and she said then that she spread his ashes over his beloved Lake Michigan. Since the water supply for Chicago comes from Lake Michigan, each of us, according to her, had some atoms of Chandra in us. Talking about life of a star. So together with quantum pressure and Chandra limit, we have now explained the HR diagram and the path that stars take on it of up to a solar mass and a little bit more. I like this version in this slide of the HR diagram because you can see actual stars there, including Arcturus, Antares, and Spica that I expected you to see when you do Lab 3. Arcturus and Antares are done for, meaning burnt out, meaning they're no longer on the main sequence. However, Spica is the star that hopefully you'll find near the planet Mars, and it's destined to have a relatively short life. Rather, short means a few millions of years relative to the Sun's, which is 10 billion. Well, what's going to happen to that star? What's going to happen to Spica? Let's go back to binding energies. In the third slide of this presentation, I've shown you binding energies of helium, carbon, oxygen, lithium. What I have here is the binding energies, only this time around we are combining lots more, and that is we're going throughout the periodic table. What you can see is that we are going to gain some E equals mc square as we're going from helium to carbon to oxygen, etc., until we reach that peak in the middle, and that peak is at iron. If we try and combine irons, we are no longer going to get E equals mc square, and that is going to tell us what's going to happen to stars. Incidentally, if you look at the right hand side of that binding energy period, you will see things like radioactive elements. If you take a radioactive element and break it so that it becomes something of a lower part of the periodic table, then you gain energy as well. That's the source of nuclear power in our nuclear power plants of present. We take uranium or plutonium, break it, and as a result we get lead, some smaller atoms, some helium, and lots of E equals mc square. In the state of Kansas, for example, we have the Wolf Creek nuclear power plant, and that's exactly what's happening over there. So what's up with that binding energy graph? What happens is that if the star to begin with is as massive and as short-lived as Spica is, it will finish with all of its hydrogen in about a few million years. But then it will have a helium core. That helium core will collapse. There'll be a small helium flash. There'll be helium turning into carbon. But then we'll have a core that's still much more massive than the Sun of carbon, and carbon will start fusing into higher elements, going through magnesium, calcium, all the way to iron. Now what's going to happen when we have an inert iron core in the very center? At that stage, the iron core will just cool off, but it's not dense enough. And when it becomes dense enough, it's still problematic because it's way above the Chandrasekhar limit. It's way above this 1.4 times the mass of the Sun for the core of iron. So we have a core of iron that's several times the mass of the Sun, and it's starting to collapse. It's starting to try and apply that quantum pressure. Unfortunately, that's not stopping it. So as it's collapsing, those iron atoms, those iron nuclei start to collide with one another. Okay? So if we have this iron colliding with another iron, they break into another element. In the process, they actually are going to yank some energy from the internal temperature of that star, which means they will cool it even further. As a result, this core, once it contracts, it doesn't increase in temperature, it decreases in temperature, less pressure. And it keeps on decreasing, keeps on becoming more and more and more dense, until basically you're left with just neutrons, protons, and some electrons hanging around, but the neutrons and protons are so close together, the density is so incredibly high, that all protons, neutrons, some electrons touch with one another. Then something fantastically unbelievable happens, which is a process kind of similar to what we started with in the middle of stars. You have protons basically colliding with other protons under very, very, very high density. In that, one proton becomes a neutron plus anti-electron. The anti-electron right away cancels with an electron. As a result, we get rid of most protons. Most of them become neutrons, and the electrons and anti-electrons disappear and give off the radiation. Now you may have remembered that when a proton became neutron and an anti-electron, something else escaped. That something else is neutrinos. Those neutrinos went through the sun very effectively without ever doing anything. But this whole process now, with these gazillion neutrinos, actually happens in a matter of milliseconds. So in milliseconds you get a rain of neutrinos rushing out, and they're probably responsible for what happens next. This very weird shaped nebula, called the Crab Nebula, is an example of a star that blew up. It blew up as a result of those outflowing neutrinos and the core collapse. We call it the back reaction, but the outflowing neutrinos that come out probably started this outflow of matter. All of those outer layers in the onion shape are thrown into space as a result of this iron core collapse. That's called a supernova. The one shown here, the Crab Nebula, is in one of the horns of the constellation of Taurus the Bull, and can be seen with a small telescope. In the year 1054, Chinese astronomers observed a new star, hence nova. Native Americans in New Mexico observed that new star. At the time, the Europeans and the Muslims, that were previously the top scientists, were too busy killing each other in the Crusades, or just before the Crusades, I'm not exactly sure, but it was a pretty bad time, and unfortunately we have no records except for China and the American Midwest. That is the supernova of 1054. At that time it shone so bright that it was brighter than all of the other stars and could even be seen during the day. There is something left in the middle of this nebula. That something, which is called the neutron star, is the topic, together with the topic of black holes, of the next lecture. This is the same exact picture of the Crab Nebula, only in the X-ray part of the spectrum, taken with the Chandra Observatory. What may be interesting is that the previous picture is fairly chaotic, whereas this picture is kind of organized. You may see a torus, and inside it another torus, and inside it some kind of a jet flowing downwards with a little bit of an angle and upwards. That is a very interesting result within that chaos, and in the middle, that slightly brighter part, when you zoom into it, will be evidence of that neutron star we were talking about. Last but not least, this is a picture of a supernova that took place in 1987. A graduate student that spent his time in Chile in an observatory at night went out of the observatory late at night for some very natural purposes. As he looked up, he noticed a star that he never recognized before. right away figured out what was happening, that there was a supernova in a part called the Large Magellanic Cloud, which is not in our galaxy but in one of the smaller galaxies that orbit ours, called the Large Magellanic Cloud. Right away he sent, at the time 1987, he sent phone messages and faxes around the globe, and people started looking for other evidence. Right away, the next day, scientists in Europe, in between Italy and France, found evidence that neutrinos arrived from that supernova. Since this is tens of thousands of light years away, the fact that we even see neutrinos so far away confirms that that many neutrinos formed as a result of protons turning into neutrons, anti-electrons, and neutrinos in huge numbers. Again, more on that in the next lecture.